of 6-point scattering, 5 and 6-point scattering and cluster algebras. So thank you, thank the organizers for organizing this wonderful meeting, this wonderful place, and also, of course, Anastasia for letting me use half of her talk, offering me to use half of our talk time to present what we have been busy with. Having found out about this on Monday afternoon, it will have to be a Blackboard talk and it will be more the discussion style, and I will ask for your help to drive the conversation in the spirit of the discussion session, which we should be doing right now. So I would like to address people who are not familiar with amplitudes, symbols and everything. So if everything is not clear, please do ask for you. So to begin with, I would like to remind you the main concepts, the key players from Anastasia's talk, which, even though it's a repetition for a limited time talk, which is, so we're looking into amplitude, scattering amplitude, namely the remainder functions of amplitudes. Amplitudes are divergent objects. The divergence break lots of symmetries, as mentioned in James's talk, the dual conformal symmetry in the Wilson loop picture, the cusp diagrams break that. But there's a nice finite quantity called the remainder, which remains when you subtract these divergences. And it, for n equals 6 and 7, so multiplicity 6 and 7 particles, it is this form, as well as in other cases, but in particular these cases. So if you compute the total differential of it, you find some functions multiplying d logs of some things. So these functions are defined as the coefficients of the d logs. And that means they are polylogarithms if they satisfy the same recursive structure with the and they end with 1. So great. So this set, the sum is over some set, and in 6 and 7 particle scattering, these are the A coordinates of GR 4, 6 or 7. And well, this has been a remarkable observation by Anastasia, Mark, and collaborators. That drove the cluster bootstrap program. If you know the amplitude as this form, then you don't need to compute Feynman diagrams, and you have you can basically guess the answer, write it down after 8 loops. So that's great, but it is restricted to these quantities. So therefore, it has been an ambition to generalize this to other quantities, so we can avoid doing Feynman. Okay. So and then. There are many ways, I should emphasize here, hinting possible directions. There are many ways in which this structure can be violated. So you may not get A coordinates, as will be the case later on, and it has been in Anastasia's talk. So you have a candidate cluster algebra to describe these arguments of the D logs, most of which are cluster coordinates, but some of them might not be. That's one problem. You might not get the logs. You might get the logs of elliptic polylogarithms, elliptic generalizations of these polylogarithms. So these are iterative integrals on the moduli space of punctured spheres, but you might get iterative integrals on the moduli space of punctured higher genus surfaces. And these are amplitudes as well. And the symbology, meaning what the arguments of these logs are, is more complicated because we have more things than the logs. So that's a very little understood situation. So these are two main ways that all the story and the missions need to be generalized. And so first we would like to go beyond GR 4, 6, and 7, baby steps. And what we start with is first baby steps. Okay, so this structure, the polylogarithms, motivates the definition of the symbol, which Anastasia also did in her talk, but since it's so important in this talk, I will write it again. So the symbol is a map of a polylogarithm to a linear combination of some words, where the coefficient of the word is a rational number, or a function, but in this case it will be numbers. Rational function of the kinematics. With the letters of the word being these cluster coordinates in the case of n equals 6 and 7 scattering. So this is how we would like to think of scattering amplitudes. And at L loop order, you have words of length 2L. In n equals 4 super-Young-Mills, it's particularly nice because all words have the same length. And in MHV amplitudes, the coefficients are rational numbers. But if you make things more complicated, like different particle contents in the scattering process, these become functions of the kinematics. Or if you go to other theories, then you have combinations of words with different lengths. But as long as you have polar logarithms, this map is defined. And it is defined as, in analogy with this equation, so you drop the logs, and recursively you compute a symbol of that and tack on this letter phi. This tensor product symbol is actually referencing to this the core algebra, core module structure of polar logarithms. So there is a co-axion motivic opposite polar logarithms, which the scattering amplitudes are, and you can iterate it. So you can iterate it a tensor product to generate these words. And the I should maybe note from the previous. It's a co-algebra co-module because it forgets about the constants, integration constants, which are the multiple zeta values. So from polylogs, whose special values are multiple zeta values, numbers are forgotten about in the symbol. Nevertheless, being able to write the symbol of a scattering amplitude is basically finding the scattering amplitude, and writing symbols of amplitudes, that is what people have been doing to compute the amplitudes. Alright, so that's the bootstrap. So we want to find symbols, but to find the symbols, we need to know what the letters are, what's their ansatz for this linear combination, what is the starting point. And that's why we need to generalize the Grassmann story. Okay, so before I move on to that, I would like to present some properties of the symbol. So firstly, any symbol won't correspond to a polar logarithm. Simply, you need to require or expect that the derivatives with respect to the kinematic variables that this thing depends on commute, and that's the integrability. The condition on the symbol. And from here, you can see roughly that the derivatives will act on the final entry of the symbol. So if you want b squared equals 0, then what this implies on your symbol are equations like that. So you take the first 2n minus 2 entries, and then replace the final 2 entries with d log phi I 2l minus 1 wedge d log phi 2l minus 1. And you have an equation for these coefficients for each independent two form and this prefactor, and this needs to be satisfied, so this needs to be 0. Okay. Well, this is the first step in symbol bootstrap. Okay, this will be. So now, why did I go into too much detail like that you would go in a lecture, not in a small talk? Because this is related to cluster algebras. If you know that your polar logarithms are clustered polar logarithms, we can satisfy these integrability conditions using clusters in a nice way. But before that, I'd like to remark that these are pairwise conditions, integrability conditions. So this part of the symbol stays the same, and the imposing integrability condition to the final two. And well, through recursion, you would have imposed integrability in the previous parts of the symbol. Or instead of doing it recursively, you can take a symbol and replace each consecutive pair of letters with the corresponding two forms and impose integrability conditions. So it's enough to know what the integrable pairs are to construct integrable multiples. And integrable pairs can be constructed from clusters. I will come to that, but I will first mention the obvious way of constructing integrable pairs. If you take a symmetric combination of letters, this is obviously going to satisfy 0 equals that. If you replace this by d log a wedge d log b plus d log b wedge d log a, it's obviously those are obvious conditions. Or if you have a cluster algebra, take a cluster, take a seat, and construct this combination. J, and then compare this with a different cluster. This I, J. And this will be integrable. This is easier to see if your B matrix is invertible. You can easily see that this is going to produce integrable pairs. So these are the symmetric pairs that you have, and these are the anti-symmetric pairs.
Should the last symbol be A, not B?
Sorry. I was looking there. Thank you. So these are the A coordinates in a different cluster, and these are in one cluster and in a different cluster. Sorry, front. Okay.
Sorry, are the BIJs the entries in the B matrix, or is it just something else? The BIJs, are they the entries in the B matrices?
The B matrices are the okay, so this is one way of solving the integrability conditions pairwise. And then you can build words. Sorry?
Are those adjacencies?
Well, so obviously these are going to be necessary. I would say at that point, these are going to be living in the same cluster necessarily. And that brings us, thank you, to the concept of cluster adjacency.
Sorry, I think the question was the two terms, do they have to be one mutation apart?
Yes.
Oh, I see. So I thought you were talking about these two things. No, you can telescope because you can get from any cluster in a cluster by mutations. You can consider sums of differences, and therefore it can take any two clusters. But I maybe steer the conversation to cluster adjacency because this is the next thing I would like to mention. Cluster adjacency. And so this is, I have time to half pass, is it?
You have time until 40 past.
40 past, okay. Right. Cluster adjacency is an observation that consecutive letters in the symbol are cluster compatible. So if you have a cluster polygon. Okay. So I'm not going to write it into the interest of time, but the slogan is here. And obviously the anti-symmetric parts of your symbols is going to satisfy that. So it's a condition on the symmetric parts of your thing. That's what I wanted to say. And I would like to give you a physical intuition for that. So take 6-point scattering. I didn't tell you, but to compute the discontinuity of a polylog, you take its symbol, you look at the branch. The symbol entries are also branch points of this polylog, the initial entries, and you pick a branch point. The discontinuity next to that branch point will have this. Will be a polylog, and the symbol of it will be what comes behind it, and in a scattering amplitude, the physical constraint is that if you compute a discontinuity of a discontinuity in overlapping kinematic channels, so if these, so these are moment to say 1, 2, 3. So first I compute disk 1, 2, 3, S1, 2, 3, and then I compute disk S2, 3, 4 of an amplitude. This is 0. So it's a very physically motivated requirement, expectation from a symbol, from an amplitude, and in symbol it will translate to S1, 2, 3 and S2, 3, 4 won't be appearing like that next to each other in the beginning of the symbol, but then this cluster algebra generalizes to everywhere in the symbol and to all cluster variables. All right. Okay. So this is something that we should be expecting from other quantities that we would like to describe using cluster algebras or partial flat varieties. And what may these quantities be? So the two main players are correlation functions of Wilson loops, which were defined in James's talk, with local operators. Like vertices x1, x2, like that. And another family of quantities is form factors. So these are like amplitudes, are amplitudes, but they have one massive leg, and they are different to amplitudes with massive legs because non-planar integrals contribute to those. And physically, they are the matrix elements of a local operator with a set of momenta. So the matrix element of a local operator with a vacuums and set of momenta. If you had an identity operator here, then that would be a scattering amplitude. So it's a generalization of scattering amplitudes. And scattering amplitudes in other theories, not dual conformal. And so the common feature of these is that they depend on the kinematics they depend on sums of momenta squared, pj minus 1 whole squared is xij squared. And translation to Grassmannians is through this formula. So this kinematic variable is a 4 bracket I minus 1 I j minus 1 j 4 by 4 minor divided by 2 brackets I minus 1 I j minus 1 j. So there's two brackets and a 4 bracket. And the statement of dual conformal symmetry is that all these cancel out. So n equals 4 super young, n equals 6 and 7 amplitudes depend on those as well. But the magic is that these 2 brackets cancel out. All you need to deal with is 4 brackets. So Grassmannian cluster algebras are the natural thing to describe this. But in general, they don't cancel out. So you need something that has 4 brackets and 2 brackets. Right? So then I would like to extend n to n plus 2. And have 4 brackets with labels up to n. Whenever I have a 4 bracket, I will identify this with the 2 bracket. I will identify this with the 4 bracket, n plus 1, n plus 2. So that is the link to partial flat variety. So these objects naturally live on F2 for these, 4 for these, n. Okay, this is the object that we're looking at. And for n equals 5, we will get F, obviously 2, 4, 5, and this is to A4. And we can ask if this reproduces the structure that we see here for all of these quantities, and I will mention this in the interest of time. And the answer is yes. So you construct all the A4 polylogs, meaning that the set where the sum runs over is the A4 A coordinates, which are 14 of them. There are 14 of them. And the n equals 5 situation, we have 31 letters, which is 20 plus 5, 25 plus 5 plus 1. These are the planar ones, non-planar ones, and one guy that keeps dropping out of quantities. So we don't watch, but it is very interesting in the Grassmannian point of view, but I'm not going to go into that. Anyway, we have 14 A coordinates here. You write a list of these, you convert them to momenta with this prescription and consider all permutations in the labels of the momenta. And it turns out you recover the 30 letters like that. And you construct all the cluster adjacent polylogs, A4 polylogs, with their permutations in the way I described. And this object is a sum of cluster adjacents A4 polylogs. Of 2, 4, 5. Right. And one thing I didn't mention with adjacency, I should have, is what happens if you have compatibility degree 1. I guess that means A coordinate is another one. It's not very clear to me what the relation between number of mutations and compatibility degrees, but I think if it's 1, that means they are mutation pair. So A and A prime are not mutation pairs, so they can't appear next to each other. So in symbol, there will be at least a gap of 1, and indeed this is allowed with gap of 1, compatibility degree 1. And you ask yourself what appears in between. And X is not for the unknown, X is for the X coordinate. So what appears is the unique X coordinate for the mutation from A to A prime. It's up to a reciprocity, but that implies a overall sign. So I don't care which way I'm mutated from A to A prime. So, and you see all this working out for these quantities. One thing that doesn't work out, which is interesting, which is a precursor of the last thing I'm going to say, which will be about 6-point amplitudes, are the supergravity amplitudes. Supergravity amplitudes, N equals 8 supergravity amplitudes, they're permutation symmetric, lack of color ordering, and they've been computed at 2 loops for 5 points, and he uses 31 minus 1 letter alphabet. And we observe all these adjacencies, we identify letters, and we observe this AXA prime, as we call it internally, triples rule. But we observe also triples of this form. This looks like my AXA prime promise. So in this story, you would expect to find a permutation of the labels that maps the letters of the supergravity amplitude into cluster variables simultaneously, all of these, where this mutates to that with these neighbors. You can't. However, W6, W12 is equal to W3, W19 plus W4, W17. So it quacks like a cluster variable, it walks like a cluster variable, but there is no permutation that maps it in the cluster algebra. So perhaps something clustery is going on. That's an evidence for something that's clustery that is going on. And this sign is arbitrary, by the way, because the letters are defined up to a sign.
So are some of the things on the right-hand side not cluster variables?
They're all cluster variables, but I can't identify a permutation on the momenta that simultaneously maps all these into cluster variables where there's a mutation from this one to that one with these neighbors.
And are you checking the cluster adjacency on the flag side or the Grassmannian side?
Well, I think of the flag as embedded into the Grassmannian, so both.
Okay, but like there would be an implication in one way. If you check cluster adjacency in flag, it will imply cluster adjacency in Grassmannian, but not vice versa.
Not looking at the Grassmannian at all, actually. Well, maybe we did as we can discuss afterwards. If there's a way out, that would be amazing if we Grassmannian. But since I am deleting nodes, I'm actually in the flag. I'm not even considering the Grassmannian. I'm just thinking of the flag as the Grassmannian because I'm more used to it. Final words on 6 points. Okay, so what happens when equals 6? So you can replace Oh, you may have asked, why is it equals 5? Because I can think of one massive momenta as two massless momenta together with some conditions. So that's why. So we have similar quantities again. The quantity that, as featured in Anastasia's talk, hexagon with the local operator.
Omer, sorry, just quickly before you move on, in the other presentation, in the F235 version, the AXA prime also works.
We couldn't make it work, sorry.
It works.
It works. It does work.
N equals 5.
Yeah, N
N equals 6, it doesn't work, sorry.
In the other presentation, what happens is, it's like GR36. The quadratics are not mutation partners. So it means they must be separated by at least 2 slots. And then there's not enough space for them to appear at 2 loops, which is correct. They don't appear.
They're antipodal in the D4 polytope for the polytope. They are on both sides, you have to do. Yeah.
Okay, thanks.
Yes, 2 loops and that. But for the N equals 5, N equals 6, you have more data, and then essentially I moved on to N equals 6. Okay, so then you can look at the analogous quantity with a hexagon for that, or you can look at form factors with 4 gluons coming out, and I think that's it so far. We don't have supergravity amplitude with 6, but it's coming, so we'll double check that as well. So what happens is you have 19 permutation classes of 200 letters, so we don't have time to go into the botanics of all the letters here. And we are missing 3 permutation classes of rational letters in the flag. I think we have one more permutation class captured compared to the spinor helicity flags that Anastasia presented. Very simple. On top of that, we for all the triples we identified, the AXA primes adjacencies work in the flag sense. And for the form factor, and algebraic letters work as described, exactly as described by Anastasia. The curious thing is that the 2 different flags give up to a cyclic transformation of the labels, produce the same discriminant as the constants, because both are embedded in GR4 states. But yeah, they give the same discriminant. And we have unidentified letters, like here. So these are identified letters, but here we don't. We have unidentified letters. Now these are the labels in the 6-point alphabet, and we have triples like that. So I've moved on to what doesn't work, but that is very teasing. It wants to work in a cluster way, but it doesn't. So all these letters in the 6-point alphabet are identifiable, apart from this W61, and W26 never appears next to W22, as if they are of compatibility degree 1. And when you look at what appears in between, there's a unique combination where they satisfy, you guessed it, an exchange-like relation. But this is not a cluster variable, and don't worry about the minus, because these are all defined up to a sign anyway. So I think with the time I have, this is all I can say, but I'm here, and so be very glad to have discussions about this.
The way we do that is we have time for 1 or 2 very short questions. In 5 minutes, I will stop the discussion. If somebody wants to stay and discuss with Omer, that's fine. Everybody else can change and go to the glacier. So, questions?
I have 2 questions. One is, did you consider maybe other types? I mean, for n equals 5, maybe like these cluster algebra are very small, so these functions that you consider coincide with many other things. Like, for example, there's the different type of bases in the cluster algebras, and like maybe lots of things are degenerate and they coincide. So for higher n, maybe the cluster structure considering there are many other options, like maybe a theta basis or other things that could I don't know, like there are other possibilities to, or maybe the dual canonical basis. I don't know, like there are different type of functions that you consider.
So he was saying that the above was all cluster variable. Are you talking about the equation below or the equation above?
I mean, those are not cluster
It's
variables.
not a better, it's not a base of.
But the one above,
Yeah.
so W6, W12, he said all of those were cluster variables.
Yeah, I
If he's in finite cluster type, then
Yeah.
all these bases agree.
Yeah, no, exactly. But then for higher n, I mean, that's what I mean. Because the problem is for n equals 6, which is not. For n equals 6, the flag variety is not finite.
Oh.
Yeah. So this is the first question. Second question is like, so for now you're just basically considering. There is a problem that flag variety doesn't have dihedral symmetry, so you're just considering like mapping it back to the same, I don't know, permutation. But then is there a way to kind of combine different, I don't know, like you take a flag variety, you permute it, basically thinking about inserting infinity twister in different positions and then doing things together in a way that there's a cluster structure that intertwines different parts of how you embed the moment.
For example, permitting momentum labels, are you talking about that, or are you talking about permitting the column labels of the matrices?
Different things.
Okay, yeah. I mean, the point is that you can, to test whether two functions are, I don't know, cluster variables or even compatible, you find a permutation that brings them in the same, I don't know, definition. Momentum permutations,
Yeah.
exactly.
Well, there are better experts to answer this way in the audience, but they might be taking you out of the positive region, and then you might be describing regions on the others outside the positive region, but that's speculation rather than a statement. Yeah. So yes, and I would like to combine everything, all permutations, in one object because it's like a patchwork.
Yeah. It's a patchwork where the things in different patches don't talk to each other for now, right? That's what I mean, that if there is a way to kind of...
Can you just state, I stated very clearly that we were missing 36 letters for 6 points.
Yes.
So first of all, you agree with our result, and then for your the way you're doing it, how many you missing?
We capture all your letters,
Yes.
all that you do, plus one more permutation class of the alphabet.
No, but how many you don't?
We counted in the permutation class way, not as number of letters, because the alphabet is given as redundant. So there are
Yes.
letters that are. I didn't think.
Is the 36 becomes what?
So I wouldn't know how to count. I wasn't comfortable counting letters because they are multiplicatively redundant. So in terms of
permutation, somewhere I can look it up. What you
there are 19 permutation classes.
Yeah, I saw that.
I'm missing 3. You're missing 4. That's way of saying.
You can point then later to the page.
What was the statement about n equals 6 then? What are you missing there?
N equals 6, well, there are 200 something letters in 19 permutation classes. And we can't reproduce 3 permutation classes, and here's an example that we can't reproduce, but it's a nice thing. And these are all positive polynomials, by the way, I have to say. They're all positive polynomials.
They're all positive on some positive response?
Yes. Some permutation of them is
They
positive.
all are, including the miss. Okay, I see.
The ones that we can't. I don't know.
Could you just label them? So I had these W's, and they went.
This is the one that we can't. There's an appendix in our paper, which is what we can do.
Because of what now going subscript on the W's I wanted, using Johannes's convention.
Yes. There's a table in our appendix with the subscripts.
Where the subscript of W's from Johannes' paper is indicated, yeah?
Exactly.
Okay. That's all I was asking. Yeah,
We can look at it together if you want.
yeah, we take a look, yeah. Thank you.
Okay, maybe I stop the discussion now, so let's take over once more.